This video is on the subject of gases. In particular, it's about Charles' Law. Charles was a Frenchman who lived in the late 1700s. He was interested in hot air ballooning, and so he needed to know, or he was interested in knowing, what the effect of temperature was on gases, because using temperature of a gas he could control the height of his hot air balloons. Here's our triangle. Remember, in chemistry class we try to relate things that we can observe or measure with what's happening to individual particles like atoms and molecules, and we need to relate those two things to the ways we can write them down in terms of equations or formulas or symbols. So in this lesson about Charles' Law, we're going to relate things that are observable, properties of gases, to an equation, how we can write them down, how we can do calculations. There's a sentence that describes Charles' Law for us. Charles' Law says that the temperature of a sample of gas, as it increases, the volume of that sample of gas increases. As temperature increases, volume increases. And another way of saying that, a more mathematical way, is that the temperature and the volume of a gas are directly proportional. When one goes up, the other goes up. When one goes down, the other one goes down. So here we can put that in terms of a little symbol here. As the temperature of a gas increases, the volume increases. Maybe a little easier to understand than that sentence. Similarly, as temperature goes down, the temperature of a gas goes down, the volume goes down. We can even be more specific than that. Here's a mathematical equation for Charles' Law that tells us that volume 1 over temperature 1 is equal to volume 2 over temperature 2. Now what's the deal with these subscripts, the 1s and the 2s? So the volume is, the volume 1, that is, the subscript 1 tells us that this is the volume that happened earlier in our scenario, at the beginning of our problem, or the beginning of our experiment. And volume 2 is what happened at the end, or later on in the experiment. Temperature 1 is the temperature that was measured at the same time volume 1 was measured. So that's the earlier temperature in the experiment. And temperature 2 is the later temperature in the experiment. The subscripts are very important. It's very important not to confuse volume 1 with volume 2, or temperature 1 with temperature 2. So here's another way that we can write Charles' Law. We can take that same equation and write it this way, and that is sometimes a little easier to deal with mathematically. So it's the same thing, same equation. Let's move it up a little bit. But now we're just, instead of having the fractions, we're just doing multiplication. So volume 1 times temperature 2 equals volume 2 times temperature 1. And either one is a good starting point for doing Charles' Law. The one on top is the way it's usually written. This one here is the way it's usually written, but this is equally good. Sometimes it's easier to deal with. Now, when we're using Charles' Law, we've got to keep a couple of things in mind. One, the temperature must be written in Kelvin. So we usually measure the temperature in science in degrees Celsius, and of course in the United States in our everyday life we measure it in degrees Fahrenheit. But when we're doing calculations with Charles' Law and other gas laws, we've got to use the temperature written in Kelvin. So here's a reminder of the formula. If we take the temperature in degrees Celsius and add 273 to it, we get the temperature in Kelvin. A couple of other things to keep in mind about Charles' Law. It only works when pressure is constant. So when we say that as volume goes up, temperature goes up, what we're saying is that that is always true when pressure is constant. If pressure is not constant, then our formula will not work. And when we're talking about Charles' Law, we're talking about a single sample of gas. That is to say, we're not adding any new gas particles, and we're not taking any of the old gas particles away. The sample of gas stays the same. So Volume and temperature are directly proportional when pressure is constant and the number of particles of gas is constant. All right, let's try a problem here. See if we can get this puppy out of the way. A balloon. Let's say we have a balloon. We fill it up with helium gas. And it has a volume of 1 liter. And the temperature at that point is 25 degrees Celsius. So we want to find out what is the volume, what happens to the volume of the balloon when the temperature increases to 100 degrees Celsius. Pressure doesn't change. All right, pressure is constant, volume and temperature is changing. Perfect time to use Charles' law. Let's look at the words of our problem. The starting volume, 1.0 liters. The temperature when the volume is that volume is 25 degrees Celsius. Remember, our temperature has to be in Kelvin. So we add 273 to find out that 25 degrees Celsius equals 298 Kelvin. Volume 2, we don't know. That's our unknown. And temperature 2, the new temperature, the temperature at the end of the problem, is 100 degrees Celsius, which is equal to 373 K. Here's our formula for Charles' law. V1 times T2 equals V2 times T1. And we can take that formula and substitute in our values. So we know that V1 is 1 liter, T2 is 373 Kelvin, V2 we don't know, and T1 is 298 Kelvin. So in red here we have our equation with the values that we know substituted in. And from there it's a matter of doing some math. Okay, so we take our equation in red. We want to isolate the unknown V2, so we divide both sides by 298 Kelvin. 298 Kelvin cancels out. On this side, the unit of measure, Kelvin, cancels out. The numbers don't cancel. They're not the same, but the unit is. And we end up with something that looks like this. V2 equals 1 liter times 373 over 298. And it turns out that the value of V2, the new volume, is 1.25 liters. So what happened to our volume? It went up. It went from 1 liter to 1.25 liters. And that's what should have happened because our temperature also went up from 298 Kelvin to 373 Kelvin. Remember we said we had to have the temperature in Kelvin to do these problems. Our volume can be in any units of measure, but V1 and V2 have to be in the same units of measure. So if we start off with a V1 in liters, we're going to get an answer for V2 in liters. Let's try another problem here. And now we have a balloon that has a volume of 3.0 liters at the start, and it decreases to 1.5 liters when it was cooled off. Now we know that the original temperature, when the volume was 3 liters, the original temperature of the balloon was 10 Kelvin. So we want to find out what the new temperature of the balloon is. And again, pressure doesn't change. Pressure is constant. The number of particles of gas in the balloon is constant. But volume and temperature are changing. Again, a perfect time, a good time to use Charles' law. We look at the words in the problem. Volume 1, 3.0 liters. Temperature 1, 10 Kelvin. Volume 2, 1.5 liters. Temperature 2, don't know yet. So we're going to try and find out what temperature 2 is. And let's do that by taking our equation for Charles' law. Here it comes. And substituting what we know into the equation. So we know V1, we don't know T2, we know V2, and we know T1. And from there, it's a matter of doing a little math. We can divide both sides by 3.0 liters. We can cancel out things that are in the numerator and denominators of our fraction, and we end up with a temperature in Kelvin of 5.0. What happened to temperature? The temperature went down. Is that what should have happened? Yes, it is, because our volume also went down. Temperature and volume are directly proportional to each other. In this problem, we used liters as the unit for volume. That's any unit of volume is okay, so long as volume 1 and volume 2 are in the same unit of measure. Temperature has to be in Kelvin. There we are. We've got a couple of examples of Charles' law, which relates temperature and volume.